Welcome back. This is the last part of section 1.2, in which I'm going to talk about limit points, isolated points, and define the boundary of a set. Okay, so first, limit points and isolated points. If we have a subset A of a metric space, and you consider a point in the closure of A, we know from proposition 1.8 that every neighborhood of X meets capital A. So we distinguish now, we have two possibilities, two mutually exclusive possibilities. Either there exists some neighborhood U of small x that meets A only at the point X. This is possible, and I will give examples now. And the second possibility, and in this case, of course, X belongs to A because it is in the intersection. Now, the other possibility is that the intersection is not equal to X, but at the same time, it's not empty. So for every neighborhood U of X, we have U intersected with A is not empty and different from X. So when I remove X, I get something non-empty. So otherwise stated, every neighborhood U of X meets A at a point different from X. Okay. Now, in this case, X could belong to A or not. Okay? It depends. Both possibilities are. So if the first possibility holds, we say that X is an isolated point of A. And by definition, it belongs to A. So an isolated point of A must belong to A. If the second possibility holds, then we say that X is an accumulation point or a limit point of A. And in this case, the limit point could belong to A or not. And I will give examples now. If you consider the subset A of the real line consisting of all the element of the numbers between 0 and 1 strictly, and together with 2. Now, here, as you may easily check, that any point in the closed interval 0, 1 is a limit point of A, whereas 2 is the only isolated point of A. It's very, very easy. Just draw a picture. And now we understand why we call 2 isolated, because we can isolate 2 by a small interval that does not meet A, or that meets A only at 2. Okay, whereas all points in 0, 1, including 0 and 1. Now, 0 and 1 are in the closure. They are limit points, but they are not in A. Whereas all points strictly between 0 and 1 are limit points of A, but are in A at the same time. So all possibilities can happen. Okay. Now, every finite set in a metric space consists of isolated points. This is very easy. So consider a finite set, capital A, consisting of distinct points, let's say x1, xn. Now, these points have distances between each other, and take for each I the smallest distance from xi to the remaining points. Since we are assuming all the elements are distinct because we are removing the redundancy, so each Ri is positive. Okay, and now it's very easy to check that the open ball of center xi and radius Ri meets A only at xi. Okay, how do you prove that? Double inclusion. Of course, xi is in A, xi is in B, xi, so on. Now, conversely, if an element x is in the ball and in A, then it must be some xj. Okay, if j was different from I, then the distance would be bigger than Ri or equal, but it is less. So therefore, xj must be equal to xi. So we have. Now I suggest that you draw a picture actually, and Ri is the biggest such radius. Actually, so anything smaller would do. So if you have finitely many points, we can isolate each one by a small ball. Okay, so this is the idea. Now, less trivial example, if you consider our friend A to be the set consisting of 1, 1/2, 1/3, etc. Now, as you know, 0 is the limit point of A, and every point in A is isolated. Actually, I think I gave this proof, this example the last semester. But you can prove that. Try to prove that as an exercise. Why 0 is a limit point? 0 is an A bar, of course, but any neighborhood of 0 contains element of A different from 0. Okay, so, and by the way, if you have a point in A bar which is not in A, then necessarily this point is a limit point, as a rule. Okay, cannot be isolated because it doesn't belong to A, so you don't need to invoke neighborhoods. Okay. And now every point in A is isolated. Why? Because the elements of A can come in a discrete way. So between 1 over n plus 1 and 1 over n, there is no other element. So we can isolate 1 over n from the remaining by the open interval, for example, 1 over n plus 1, 1 over n minus 1. Okay, so draw a picture. The set of integers has no limit points of R. All points are discrete, are isolated. Okay, in this case, we say that the set is discrete if all points are isolated. Okay, try to prove that. It's very easy. Now, what are the limit points of Q? The limit points of Q, we know that Q bar is R. Okay, but here, unlike Z, no point of Q is isolated. So all points of R are actually limit points. Okay, because if you take any real number x and you take in a neighborhood x minus epsilon, x plus epsilon, then x minus epsilon, x plus epsilon contains infinitely many rational numbers. So it cannot be, so it meets Q at points different from x. Okay, so this is straightforward. So this is unlike the Z. Okay, whereas in the case of Z, you can take, for example, if you take n in Z, n minus 1, n plus 1 open meets Z only at n, because between n minus 1 and n plus 1, there's only one integer. Okay, next result. If A is a subset of a metric space and small x is the limit point of A, then actually not only every neighborhood of x meets A at a point different from x, but actually the intersection is infinite. Okay, so if you go back to the definition states that for every neighborhood U of x, the intersection, if you remove x from the intersection, we get a non-empty set. But actually, it's not only not empty, it's infinite. And I gave this as an exercise. So try to pause the video and try to solve this, to prove that on your own before we prove it. Okay? It's very important. Okay, and now the last topic of this video is the boundary of a set. Now we talked about the boundary in a very intuitive way, but now we have a precise mathematical definition. The intuition behind the concept of boundary is the boundary is something that is at the limit of the set, or something between the set and its complement, if you like. Okay. Now the boundary need not be contained in the set if the set is not closed. Okay. And it could be a part of the set. So actually the boundary is a part of the closure, but at the same time it's it's a part of the closure of the complement of the set. Okay. Now the closure of the complement is just the complement of the interior. So we define the boundary of a set as just being the closure without the interior. Or if you like, in an equivalent way, it's the intersection of the A bar and the closure of the complement of A. Okay, so by definition, it's a closed set because I'm removing an open set from a closed set. Okay, so this makes sense now. So, and as usual, let us give some examples. As you expect, the boundary of the closed interval 0, 1 is, we go back to the definition, the closure is closed, so it's 0, 1. The interior of 0, 1 is 0, 1 open, so we just get the two endpoints 0 and 1. Okay, and we can take, instead of 0, 1 closed, we can take 0, 1 open or semi-open. It's exactly the same thing. Okay. The boundary of Q is less intuitive, but if you go back to the definition, the boundary of Q is Q bar without the interior of Q. Q bar is R, and the interior of Q is empty. So get R without the empty set, so it's R. And we shall prove in the exercises a very general result saying that, and this corresponds to our intuition, if you take the open disk of center 0 and reduce 1, as you may expect, the boundary of this open disk is the circle. So here we distinguish between disk and circle. The circle is the boundary. The disk is what is inside. Okay, and this corresponds completely to our intuition of boundary of a set. So the less intuitive result is this one, the boundary of Q, because Q is a very complicated set. Okay, so we have to be careful when we deal with the concept of a boundary. It's not always intuitive. Now, I will end with two remarks. The boundary of a set is always closed. We said why, actually, because we remove an open set from a closed set. So get a closed set. And second thing, when is the boundary empty? The boundary is empty exactly when a bar equal to a circle. And a bar is equal to a circle happens exactly when A is both open and closed. Because a circle is open and a bar is closed. So A is in between. If a circle equal a bar, so we get a bar equal a circle equal A. So A is both open and closed. Therefore, the boundary of the whole space is empty, and the boundary of the empty set is empty. Okay? Now, and as we said, there may be other clopin sets other than these two extremes. And this happens when the space is not connected. And this will be the subject of chapter 4. Okay. So this concludes section 1.2. And in the next video, I'm going to solve some exercises. So thank you for your attention.